Great, thanks very much, John, and thanks to the committee for the invitation to speak. As we've heard from a couple of the other speakers, Sarah and Quiva earlier, GSI's groundwater geothermal unit are involved in a range of different policy areas, I guess. And this afternoon, Ted and I are going to share a presentation, and we're going to talk, Ted, about climate action and me about the work we're doing in drinking water. And as always, this is very much a team effort, and Ted and I are presenting on behalf of our colleagues in the Groundwater 3D team and the Groundwater Climate project team. So it's just a picture of, I hope, everyone in the two project teams. So I'm going to give an update on the Groundwater 3D project. I'm conscious that Robbie Meehan presented the project at this conference a couple of years ago when we were getting started. But for those of you who don't know, the Groundwater 3D project is a catchment-based assessment of groundwater resources. The aim is to identify groundwater resources that could be used to provide long-term sustainable groundwater supplies. So similar to what Paul's just been talking about. The project was initiated after discussions with Irish Water, and it focuses on public water supplies. But, you know, a lot of the work would be relevant, you know, as well as to Irish Water, to the group water schemes, or to really anyone that's looking to put in a larger groundwater supply. And we've been working closely with the EPA throughout. We're in the fourth year of a 4-year project, and we have been studying the 32 catchments in the east of the country that you can see on the map on the right of the screen. And our plan would be, after this year, to roll the methodology out to other catchments across the country, funding dependent, of course. The output from the project are reports for each of the catchments, and you can see the report covers there on the right. Prioritized list of groundwater resources, and then field verification. And those reports and various documents will be published soon on the GSI website. So why did we start this project? So we've heard from other speakers, notably Rick, and just now Paul, of the increasing pressures on water resources. So increasing population, supply-demand deficits, impact of climate change. And this is becoming a reality in Ireland. So the slide shows the climate change predictions for Ireland, and then also press coverage for the impacts of pressure on water resources. So there's, you know, a need to better understand Irish groundwater resources, and from our point of view, for drinking water. And in that way, the project fits quite well with the theme of the conference and the World Water Day, making the invisible visible. So our aim is to make groundwater in Ireland more understandable. So the approach that we use has got 4 steps. The first is to identify the groundwater resources within each catchment. The second is to look at any potential constraints that need to be considered to developing a groundwater resource in that catchment, compare across all of the catchments and prioritise, and then carry out field work to verify and quantify. And most of the rest of my presentation will follow those 4 steps. And just to mention before I get in to the details, perhaps slightly unintuitively, we are using surface water catchments as the units for our study. And the reason we're doing that is so that we have a calibration point, so we can compare how much water is coming into the catchment via rainfall and how much is leaving, either as flow out to the sea or to other catchments. And that allows us to understand the split between groundwater and surface water, and we have a water balance for each catchment where we look at that split. And also, importantly, it allows us to study the cumulative impact of abstractions on the water resources within each catchment. So the first step, which I mentioned earlier, is identifying the groundwater resources. And we're basically doing that with any readily available, relevant information that we can use. So the figure, the slide shows GSI maps that we use just as an example. So the geology, the hydrogeology, the recharge, etc., etc. The groundwater levels from the EPA in the hydrograph, and we're using Met-Éireann data, rainfall, evapotranspiration, to try and understand the effect of rainfall. And we're combining all of that data in a consistent manner in each of the catchments to develop a conceptual model. So this is the Boyne catchment. We've split the Boyne up into 5 conceptual zones based on the hydrogeology. So the groundwater flow and the way the groundwater is behaving is different in each of those 5 zones. And we've identified that southeastern zone as a zone with most groundwater potential. And then the next step is to think about potential constraints to any future groundwater resource in that catchment. So we're considering things like groundwater considerations, ecological considerations, existing abstractions, what's the groundwater chemistry like, and the impacts of climate change. And we're looking at those in a special way. So here we have the Boyne catchment again, with the area with better groundwater potential in the bluey purple, and then the rest of the catchment is shown in white. And it's not that there's not groundwater resource potential in those white areas, it's just that that resource would be local or domestic potential. And then we add in the various considerations. So you can see the hatched areas. So within each of those hatched areas, there's something else, a different thing to be considered, whether that's the hydrogeology, the ecology. And it's not to say that those couldn't be developed, it's just we'd have to consider those different constraints or considerations. So the areas left, which are unhatched in this map, are the areas that we consider to have the greatest groundwater resource potential without potential constraints. And then the next step is to carry that out across all of the catchments and prioritise. So you can see the Boyne catchment there within the whole study area, and we've carried out the conceptualisation. So you can see the purpley blue colour are the areas that we consider to have better groundwater resources, and the white areas to have domestic or local supplies. And then we've added on top of that the various considerations that we'd need to make across the study area, and that allows us to prioritise the groundwater resources across the area. And I'll just add that we haven't, we'd wanted to include the upcoming abstraction legislation, but that hasn't been published yet. So at the minute that's not included, but once that legislation has been finalised, then we can add it in. And then step 4 is looking at fieldwork to verify and quantify the resources. So we didn't want this to be a purely desk-based study. We wanted to be able to verify it and to get a handle on aquifer properties, abstraction yields, groundwater chemistry in the different settings that we were identifying. So we've looked at studying, doing fieldwork in different areas, and I'm going to just quickly go through some of the work that we've been doing in Oak Park, which is in the Barrow catchment there in yellow. So firstly, I'd like to mention Chegist, who have been really helpful in accommodating the fieldwork, so many thanks to them. Oak Park is a research farm, so there's already some boreholes. We've mainly Natalie Duncan and Alistair Pilmer have been carrying out this work. So they've put in loggers so we can understand the groundwater levels at the site, and you can see the winter recharge there in the hydrographs on the left. We've done some augering to try and understand the depth of the sand and gravel aquifer above the limestone aquifer. And we've more recently carried out ERT geophysics survey to get a better understanding of the 3D nature of the sand and gravels. And our next step will be to drill and pump test a couple of long-term monitoring boreholes to understand the groundwater resources in this type of setting. And just before I hand over to Ted, I just wanted to highlight the National Groundwater Chemistry Database, which Sean Wheeler gave a really good presentation on earlier. This is also being carried out by the Groundwater 3D team. So there's a number of many data points have been processed, and a web app that allows you to interrogate the data. So from that, I'll leave it there and I'll hand over to Ted. Thanks very much for your time.
Thanks, Ted. Yeah, okay. So thanks, Katie. I'm going to go through GW Climate. First, I'll just go through the project in general, and then I'll just summarize some of the main products and analyses that we're working on. The project is a 3-year study to investigate how groundwater resources respond to climatic stresses and improve the reliability of planning and forecasting. We're talking about the impacts of groundwater flooding and groundwater recharge and droughts, consequently. It's a collaboration with the Institute of Technology YTCarla. We have a researcher embedded there, or an association with a researcher in YTCarla, and it's continuing on some of the aspects of the GW Flood project, which ended in 2019. The objectives of the project are to identify groundwater systems susceptible to climate change dynamics, to assess the vulnerability or resilience of aquifers to climate change, to extend current national groundwater monitoring to capture climate change dynamics, and to model future groundwater dynamics to improve our understanding, and develop hydrological outlook and groundwater flood forecasting tools. The themes in which I break it up are evaluating groundwater susceptibility to climate change, monitoring the impacts, and modeling the impacts. And in terms of this talk, I'm going to talk about our work on drought susceptibility and trying to make a map of it, standardized groundwater index, the monitoring network we're trying to put in place, and our modeling work, including hindcasting, forecasting, and climate change analysis. First up is the drought susceptibility. We are looking at this in the frame of storage and autocorrelation. We're seeing if we can quantify the drought susceptibility via groundwater storage, and to do this, we are using the autocorrelation function. So we are calculating the autocorrelation at all possible boreholes we can get our hands on, the EPA sites and the GSI sites. We have 133 in total that we were able to run on, and we calculate the autocorrelation lag for all of these sites. And that's great for each of those sites, but we want to have a stab at making a national map. And to do that, we turned to machine learning, specifically the random forest model, which can predict the lag time across Ireland. Well, the plan is to predict lag time across Ireland using all available GIS data sets, such as DIM, vulnerability, depth of bedrock, etc. And there's a draft map that we have in place already. It's currently submitted to the Journal of Hydrology and it's under peer review at the moment, so I'm looking forward to see what comes back about the map. Secondly, the standardized groundwater index is something we want to do. It's very similar to the standardized precipitation index or standardized streamflow index, but it's for groundwater, obviously, and it was developed by the British Geological Survey in 2013, and it's a really useful tool for basically normalizing all the groundwater data sets to the same reference base, really, and you can quite easily pick up on when was a drought or when was above normal conditions. One of the issues we have, however, is the length of record available, because you use the data set to normalize against itself when you calculate the SGI. And I mean, that's similar to how you would do it with the SPI, but you should really have about 30 years of data to do that. And we don't for groundwater, so we have to look at a bit of modeling to try to fill that gap, and I'll get to that later. So moving on to monitoring, we are looking to establish a monitoring network that allows us to assess the specific hydrologic dynamics, the context of climate change pressures. It's been designed to represent the spectrum of hydrological environments and to record any relevant processes with regards to drought, groundwater flooding, groundwater surface water interaction, and coastal interaction. Ideally, we want minimal anthropogenic influences, like there to be some susceptibility to climate change processes, and the land to be public, and that's just for practical reasons. It's much easier to deal with public land, or so we thought at the start. We have sites lined up in Dublin, South Galway, Longford, Offaly and Wexford, and we hope to be drilling starting next week. The other little point I want to make is we've gone and recovered old historic chart records from the GSI archive, and we will have them up on our groundwater level viewer in the coming few months. So that's gwlevel.ie, I was curious. Then the last thing I want to talk about is modelling. The goals of the modelling is hindcasting, to reconstruct records, forecasting and outlook, both short-term and medium-term forecasts, and climate change analysis. And we're doing this in parallel studies between Geological Survey and YTCarla. In the Geological Survey, we're working on the EPA and GSI monitoring stations using more established modelling packages. We're starting with Aquamod, which is a BGS package. And then in YTCarla, they're developing and expanding on the modelling approaches used in the groundwater flooding project, and they're targeting turlocks first and then hopefully moving on to groundwater after that. Aquamod is a lumped modular conceptual model developed by the BGS, and it's used as part of their national hydrological outlook. It simulates groundwater level time series by linking simple algorithms of soil drainage, unsaturated zone flow, and groundwater flow. It takes in rainfall and PET and outputs simulated groundwater levels, and it's quite a nice package, and we're getting good use out of it. These are the sites we've used it on so far, over 100. I can't remember the exact number, it's in the proceedings, but I've split it up there into green and red dots. The green dots are the sites that we are, well, they have NSE values, National Sutcliffe efficiency values of above 0.75, so reasonably happy with those calibrations, and the red sites are the less happy calibrations so far, so more work to do on those ones. In terms of YTCarla, the models are different. They're running a transfer function model and reservoir models. I won't go into the details just to save time, but these are the sites that they've ran their models on so far. There has been a lot more turlock models made in the GW flood project, but now the YTCarla work is focusing on these 17 sites to enhance the models and then expand them back out again to more sites. So what we want to do with it is hindcasting. We want to look at historic variability of groundwater and groundwater flooding back as far as we can generate data for realistically. And then also, as I said before, with the SGI, I want to at least get 30 years of data, at least, in order to run an SGI to have it more realistic. We also want to do flood forecasting, so that's short-term forecasting, which is linking precipitation forecasts with the turlock models developed by YTCarla, and that'll be really useful in situations like the plot there on the left, Ballycar, County Clare, where the railway gets flooded and closed by a turlock. And it will be very useful information to know when that might happen, and also if it's flooded, when it might not, when the floodwaters might recede. Then medium-term estimates as well, and this is where we take historic records, we take historic rainfall and apply it to a current scenario. So in this example, that's Loch Funchna and County Roscommon, where in October 2021 we applied all the historic rainfall in individual years and pretended it happened in October 2021 going forward, and you can see the change, the different responses that we can see, and then we could start to draw some statistics out of that to think what might happen based on historic rainfall. And the last analysis is the climate change stuff. We are looking into scenario-led and scenario-neutral analysis, but I'll start with scenario-led. Actually, I'm only going to talk about scenario-led because that's what the work has started with so far. This is where we take ensembles of synthetic precipitation and P data provided by iCheck climate models, and we put it directly into our groundwater models. The data comes from 5 regionally downscaled global climate models. We've got data for 3 representative concentration pathway scenarios, RCP 2.6, 4.5, and 8.5. We only really run 4.5 and 8.5 because that's what's realistic these days. Then we have the data from 1980 to 2100, and we run it through our models. We used 1980 to 2010 as the reference period to say what current conditions are, and then we see how it might change in the future. And the results are preliminary, what I'm going to show here. This is how we show it quite broadly. This is a flood duration curve at Ballycar, Turlock, which is the one that floods a railway I mentioned earlier. So we have the black curve here shows the volume of the Turlock versus the proportion of time it's at that volume. So over on the left, we have high volumes for very little time. And over on the right, we have low volumes, and it's at that level or above for a lot of the time. And so the middle value, the y-axis peaks at 1 there for this curve, because that is it's normalized to the peak of the reference period being value of 1. And you'll see what's going to happen now when we bring new years. We move the window from the reference period up year by year, up towards the end of this century, and draw a line for each of these new 30-year windows as we move forward. The blue being the current scenario, and the red being the future. And we can see that the flooding is getting deeper and more long in duration as we go into the future. If we draw a line here, which is actually the level of the railway, we can see that the current situation says the railway will flood about 1% of the time, that's about what we're experiencing. RCP 4.5 will predict that railway will now flood 5% of the time by the end of this century, which is a big change. And then if we go to RCP 8.5, which is the more pessimistic view of emissions targets, that'll be 10% of the time. So that'll be 1 year out of every 10 years, the Western Railway corridor will be flooded, which is pretty bad news. And this trend is seen across the board in nearly all the Turlocks that this has been run on, some more so than others. We've also ran it on groundwater on a few of the sites. Here's Druids Glen Monitoring Station and Muchgrange Fence, both EPA stations, and we see similar trends. What I find quite interesting is the top left plot here. You start to see the red lines, so that the future lines dip below the blue lines on the right side of the plot. That indicates this model predicts more time at lower groundwater levels towards the end of the century, as well as more time at higher groundwater levels on the other side of the plot. So an amplification of what we're seeing now. And then, so that's basically it. I just want to stop my presentation on one final, slightly unrelated slide about seasonal flood maps. These are a new product we developed. We have predictive flood maps and maximum historic flood maps, which we released in 2020, but now we've developed SAR seasonal flood maps. So it's using the same process, remote sensing, Sentinel-1 imagery. We have maps for each year from 2015 to 2021, and that's on the GSI website now. So that's